So now let's talk about negative aspects of hydropower. So one of the more obvious ones is the vulnerability of hydroelectric dams to drought. So hydropower production is directly dependent on hydrology or stream flows. And so what that means is that when reservoir inflows decline during drought, then the availability of hydropower declines. And so usually generation at hydroelectric dams and reservoir inflows are highly correlated. So this data is from a hydroelectric dam on the North Carolina-Virginia border that's owned by the federal government. And what we see is that years when inflows are really high, the dam produces a lot of electricity, and then during years when inflows are low, the dam produces very little electricity. And so the same is true in California. California is a state that doesn't rely on coal much because of strict air quality requirements. So most of the state's generation capacity is natural gas. A significant part of it is hydropower. But when the state goes through periods of drought, that is compensated directly by natural gas generation. And so that's what this figure at the bottom shows. Anytime you see hydropower increasing, natural gas is decreasing. Anytime you see hydropower decreasing, natural gas is increasing. So this has a couple of important implications, and that is that reduced hydropower tends to mean higher emissions. So this blue figure is the Palmer Hydraulic Drought Index. So it's a measure of drought. So the higher value means wetter, and a lower value means drier. And the black line shows the percentage of electricity demand in California that's being met through fossil fuels. So these are negatively correlated. So the more water you have, the less emissions you have, and the less water you have, the more emissions you have. Less hydropower can also impact market prices for electricity. So if you think about the placement of hydropower in the system supply curve, it tends to be at the bottom left because the marginal cost of electricity from hydropower is zero because there's no fuel cost. And so that means that when you lose hydropower, the system supply curve shifts inward to the left. And as long as we assume demand is staying the same, if the system supply curve shifts inward to the left, the intersection between supply and demand occurs at a higher point on the y-axis, and you can get increased price of electricity in the wholesale market. So drought tends to increase the price of electricity in wholesale markets, and that's part of what happened in the California electricity crisis in the early 2000s. So now let's talk about environmental impacts of dams. So dams profoundly impact aquatic ecosystems by altering the physicochemical properties of rivers. They tend to reduce the temperature of water in rivers, so they are often storing water and then releasing water downstream from the bottom of the reservoir, which might have colder temperatures. They tend to impact the nutrient content and potentially also dissolved oxygen content of rivers as well. Geomorphology, so they can increase channel erosion and bank erosion downstream. They also withhold sediment, so they trap sediment that needs to be transported, potentially nutrient-rich sediment that needs to be transported downstream. So these are all very significant environmental impacts. Actually, my first research job in college, I was working with a PhD student in the Department of Environmental Engineering at UNC Chapel Hill to look at the biogeochemical impacts of dam removal. So because of some of these environmental impacts, there has been an increased push in the United States to remove dams, especially ones that are not providing hydropower, that might be trapping nutrient-rich sediment and disrupting life cycle processes of fish species. So the job actually involved a reasonable amount of field work in a wetland in Johnston County, North Carolina. The work itself, the research itself was interesting, although I have to say the work itself was awful because I was in a wetland in North Carolina in the middle of the summer. Wetlands are extremely ecologically important, but kind of miserable to walk around in, especially in the summer in North Carolina. So this is one of the things that spurred my interest in computational modeling, so I have not done any field work since. So other impacts of dams on rivers include changes in hydrology, especially changes in what we call flow regimes. So the magnitude, duration, frequency, rate of change, and timing of river flows. So these are actually really important for sustaining and promoting the success of native species in river ecosystems. So if you if you fundamentally alter stream flow patterns, you can significantly impact downstream river ecosystems in a number of different ways. So we're going to talk about that more in just a minute. Before we get to that, I mean, one of the more fundamental impacts that dams can have on the life cycles of anadromous fish is by providing serving as a physical barrier that keeps adult fish from traveling upstream in order to spawn. So the life cycle of anadromous fish, in many cases, involves them being born in freshwater systems, and then traveling from an estuary into a marine environment where they grow up and become adults. And then in order to reproduce, they leave the marine environments and they go back into the freshwater system in order to spawn. And so if fish can't go upstream from the marine environment to the estuary to the freshwater system in order to spawn, then they can't reproduce. And so that is a significant threat for the life cycle of these types of fish. Contrary to popular belief, hydropower turbines don't actually damage a vast majority of juvenile fish. The baby fish that are born in freshwater systems are quite easily able to pass downstream. Even flowing through hydroelectric turbines, in many cases, doesn't significantly damage juvenile fish. The problem is really getting the adult fish upstream. If there's a dam, if there's a physical barrier in the way, it becomes very hard to go upstream and spawn if you're an anadromous fish or diadromous fish. And so there are a number of different strategies for trying to allow fish to go upstream, including fish ladders. This literally involves fish jumping one step at a time up a river over an entire man-made dam. So if you're skeptical about the success of these systems, you're sort of right. They do kind of work. They're better than nothing, but certainly not as good as having no dam in place. Back to this issue of flow regime. So exploiting one of the issues with hydroelectric dams, in particular the conventional dams that are strategically controlling the storage and release of water downstream in order to maximize the value of hydropower production or provide flexibility to the grid. Operating in this way can significantly impact a river's flow regime. So again, the timing, magnitude, duration, frequency, and rate of change of river flows. One of the things this can do is it can eliminate big floods. We build dams partially to eliminate big floods. However, big floods from an ecological standpoint are super useful. They weed out non-native species. So if you've evolved over thousands, hundreds of thousands of years as a fish or macroinvertebrate, to expect occasional really big floods, having the ability to cope with that actually improves your rate of success because it can weed out non-native species that might not have evolved. And so eliminating big floods in some cases can allow non-native species to come in and outcompete native species if you take away that source of stress. Dams also can cause abrupt changes in flow that damage habitat and strand fish in floodplains, and this is associated with hydroelectric dams operation as peaking resources. So if we have electricity demand going up and down and up and down and up and down, and we know that we want to use hydroelectric dams to maximize the value of electricity that's produced, we're only going to produce electricity during the highest value periods of the day. And so what that means is that river flows kind of look like this green line, where they're either really low or they go from almost nothing to extremely high flows very quickly, and then they're at really high flows really quick, for very high flows for a little while, and then they ramp down to nothing again. And so this is in stark contrast to what natural stream flow patterns would look like in a river if no dam were present. So if you're a fish or a macroinvertebrate, it's a little bit like living downstream of a fire hose that's being turned on and off, which most organisms have not evolved to be successful under. So because of all the impacts of conventional hydropower on river ecosystems, when we think about using hydropower to meet, for example, renewable energy mandates like portfolio standards REPs, typically most states will only allow a small fraction of conventional hydropower capacity to be considered. So if the state of Oregon says we want to meet 30% of our generation or electricity demand with renewable energy, they may count 10% of the state's hydropower capacity towards that goal. Other potential environmental impacts from hydroelectric dams and reservoir include methane emissions. So the process of building the dam, remember, means that you are flooding very large spatial areas behind the dam. And so the organic matter, the biological matter that is submerged, can decompose. And as it decomposes, it may release methane into the atmosphere. And so this is a source of great uncertainty about what methane emissions from new hydroelectric dams are. And the general research that's come out about this suggests that the placement, the siting of hydroelectric dams matters. If you're building reservoirs in tropical regions, where there's a lot of biomass and organic matter that would be submerged, and then higher temperatures that would increase the rate of decomposition potentially, then the amount of greenhouse gases that would be associated with the methane emissions over the lifetime of the hydroelectric dam might be greater than the same emissions that would be producing an equivalent amount of electricity from a coal-fired power plant. And then, of course, one of the other issues with building large reservoirs is the human displacement issue. Not only do dams impact the environment, they also impact people. So this has been most notably true, I think, with the construction of extremely large hydroelectric dams in China, including the Three Gorges Dam, which has displaced 1.3 million people. So all the people that lived upstream of the dam along the Yangtze River had to move. And I think forcibly moved. Now this dam is gigantic. Its installed capacity is 22,000 megawatts. So this is larger than the entire legacy Duke energy generation portfolio. It's about the same amount of electricity, hydropower capacity that's owned by entirely by BPA in the Pacific Northwest. So existing hydropower capacity today, China is the leader, followed by Canada, Brazil, and then the United States. You can also get a sense for the percent of generation that comes from hydropower in each one of these countries. And so there are some countries, take a look, that are extremely reliant on hydropower. Notable examples would be Brazil and Norway. So this list looks a bit different when we're talking about where we might think about adding new hydropower in the future. And so the leaders here are China and Brazil and India. So you might wonder why no new capacity is being planned in the United States. Now remember, the best places to build reservoirs are where there's steep geographical relief and narrow river outlets. So places like this, where we built the Hoover Dam on the Colorado River. In the United States, 75,000 dams already exist in the United States, and we've already used all the good spots. There are really not many places that fit all those criteria anymore. In addition, the places that might be possible to build new dams, the construction of new dams is unlikely, partly due to increased regulations and increased environmental awareness around dams' impacts. So it's very unlikely. It's similar to whether utilities will build new coal-fired power plants in the United States. Building new large hydroelectric dams in the United States is almost guaranteed not to happen. Okay, this was the last lecture on conventional energy technologies. Now we are ready to move on to renewable energy and the future of the grid, for better or worse. So next time we're going to talk about wind power. Note that homework 5 has been assigned.